Hello and welcome to a new video on IGCSE Mathematics. In this video, we shall be discussing nonlinear sequences. We will begin with quadratic sequences. Find the nth term of these sequences. So in this case, you are not actually told in advance that this sequence is going to be quadratic. So you have to figure out a way to identify whether this sequence is a linear sequence or a quadratic sequence or a cubic sequence or any of the other types that we're going to study in this video. In the previous video, we discussed linear sequences, and we said that if the difference between each two terms is the same, this is a linear sequence. So we begin by checking the difference between the first two terms. So to go from 4 to 8, what do we need to do? We need to add 4. And then to go from 8 to 14, we need to add 6. And then from 14 to 22, we need to add 8. So the difference here is not common. However, if we look at this sequence of differences and we get the difference between each, we're going to see that from 4 to 6, we have +2. From 6 to 8, we have +2 as well. So the idea here is that the second layer of differences is actually common. You have the same number on the second layer. So this tells us that the sequence here is quadratic. Quadratic means it has n power 2. In the formula of the sequence, we have n power 2. So let's start by drawing a small table here and comparing n and n power 2 in general, regardless of this question. So when n is 1, n power 2 is 1. When n is 2, n power 2 is 4. 3, 9. We can even add 4 and 16. So we now have the basic values of n power 2. These are fixed. These have nothing to do with this question. Now we're going to add another column for the elements of this particular sequence. We're going to list down the sequences, the elements, of this sequence. So let's write here un, and let's just put the values of the sequence. So we have 4, and then 8, and then 14, and then 22. We need to figure out what the relation is between n power 2 and the elements of the sequence. So from 1 to 4, what do we add here? We add 3. From 4 to 8, we add 4. From 9 to 14, we add 5. From 16 to 22, we add 6. So you can see that there is a pattern here. The sequence terms are related to n power 2, and the pattern is that we keep adding 3 and then 4 and then 5 and then 6. We want to express this using a sequence. So we have a sequence of 3, 4, 5, 6. And we can tell that this is obviously a linear sequence because we have here +1, +1, +1. So we can use the formula for a linear sequence here, and we can refer to the previous video. If you don't know how to write the formula of a linear sequence, you can watch the video on linear sequences. So un equals an plus b. A here is the common difference, which is 1. We put n as 1 as well. And we put un as the first term of the sequence here, which is 3. So 3 equals 1 plus b. So therefore, b equals to 2. So our formula is going to be un equals n plus 2. This is the formula that describes the sequence in red in this table. So this is here n plus 2. And we understand that n squared plus this sequence gives us our sequence. So therefore, n squared plus n plus 2 gives us the sequence un, which is what we're trying to figure out. So therefore, our final answer is n squared plus n plus 2. And this is the correct answer here. Find the nth term of each sequence. Of course, we already know in advance that this is quadratic because this is the title of this part of the video. However, in the exam, you don't know that in advance, so you have to figure out what type of sequence it is. And the first thing you do is you just figure the relation between each two terms. So here we have +7, here we have +9. Of course, if you don't understand how I got these numbers, you subtract in the opposite direction. So 16 minus 9 is 7. 25 minus 16 is 9. 36 minus 25 is 11. So here we have +11 and so on. If we get the second layer of differences, this is +2 and this is +2 as well. So therefore, since the second layer has the same number in each, it's always +2. So this, we know that this is a quadratic sequence. So quadratic sequence means that it's related to n power 2. So we have here n and n power 2. And we want to figure out the relationship between n power 2 and un, which is the actual sequence in the problem. So we just begin by listing down the first few elements of n, which are always going to be 1, 2, 3, 4. And here we have 1, 4, 9, 16, which is basically n power 2. So we're raising each element to the power of 2. And then we write down the elements of un, which are 9, 16, 25, and 36. Now we want to figure again the relation between n power 2 and un. So 1 plus 8, 4 plus 12, 9 plus 16, and 16 plus 20. So the sequence that describes the relationship is going to be 8, 12, 16, and 20. Of course, if we analyze the sequence on its own, we can easily see here that we have +4, +4, and +4. So this is a linear sequence. So un, or so as not to confuse this with the actual sequence, let's just call this anything else. Let's call it like wn or anything. So wn here is equal to an plus b. And we know how to deal with a linear sequence. We put n here as 1. We put wn here as the first term, which is 8. And a is the common difference, which is 4. So 8 equals 4 plus b. We take the 4 to the other side. So 4 equals b. So wn here, the sequence is 4n plus b. So 4n plus 4. So b is 4, so 4n plus 4. This tells us that the sequence in blue in the table is actually 4n plus 4. So, and we know that this is here n squared. So n squared plus this sequence gives us un. So therefore, the final answer is this whole expression here, n squared plus 4n plus 4. This is the final answer. Of course, using very basic algebra, you can rewrite this as n plus 2 all squared, but this is not necessary. Both of these answers here are going to be correct. They chose the factorized form. They wrote n plus 2 all squared, but like I said, both answers in circles are considered correct. Next, we move on to cubic sequences. Find the nth term of each sequence. So like I said before, you don't know in advance whether the sequence is going to be linear or quadratic or cubic. And the best way to test is to just figure out the operation we need to move from one term to the other. So here I have +7, and here I have 28 minus 9, which is 19. 65 minus 28, and this is 37. 126 minus 65, and this is 61. So we're adding very strange numbers here. Let's try the next layer. So 19 minus 7 is 12. 37 minus 19 is 18. 61 minus 37, that's 23. excuse me, that's 24. Now, we still don't have the same number. So we add again, so we try to figure out the next layer. So the next layer is from 12 to 18. Excuse me, I forgot to put a plus sign here. Anyway, so from 12 to 18, we have plus 6. And from 18 to 24, we have plus 6. So if the numbers here are all the same, it's linear. In the second level, if the numbers are all the same, it would be quadratic. But in our case, the numbers are actually the same in the third layer. So therefore, this is a cubic sequence. Now that we know that this is a cubic sequence, the rest is very easy. The rest follows quite simply. All you have to do is just repeat what we did in the quadratic case, but for the cubic. So we're just going to write n and n power 3 and un. N is 1, 2, 3, 4. N power 3 would be 1, 8, 27, and 64. Now we want to write un first, so 2, 9, 28, 65. Here the relationship is very simple. Don't even need a sequence for it. It's always going to be plus 1, plus 1, plus 1. All of them are plus 1. So to get un, all we have to do is write write n power 3, and then plus 1 equals un. So therefore, un can be written as n power 3 plus 1. And this is your final answer. So this is an example of a cubic sequence because, of course, it was harder to figure out that the sequence is cubic. So they gave us an easy relation for the part of the table because the first part was much harder than the quadratic case. So the second part was much easier. Anyway, so n power 3 plus 1 is the correct answer. Next, we move on to a type of sequences called exponential sequences. So here, the plus operation will not really help because in this case, no matter how many pluses you do, it will not converge into a common difference. But you can actually think of the times operation as well. So one of the things you need to test is whether if I multiply by the same number every time, do I get a correct result or not? So from 1 to 3, we have here times 3. Here as well, we have times 3. Here as well, we have times 3. So this is what we call an exponential sequence. An exponential sequence basically has the formula a power n times b. So un is equal to a power n times b. Now, what is a power n here? The a is the number that we got, sort of like the an plus b and the common difference. So the a is simply the 3. So un equals 3 power n times b. And we want to figure out what the b is. Of course, this would be quite simple to do. All you have to do is just put n equals 1. So if we put here n equals 1 and un is the first term, so 1 equals 3 power 1 times b. And therefore, 1 over 3 equals to b. So the answer is un equals 3 power n times 1 over 3. Of course, this can be simplified using your knowledge of exponentials. Un equals 3 power n over 3, and you can subtract the powers. So this is like 3 power 1. So this becomes 3 power n minus 1 as a final answer. And 3 power n minus 1 is the correct final answer. Again, here we have a sequence. You can try adding and getting the differences, or you can try multiplying. Here, if I multiply, I can immediately see that I always have times 2 here. So the sequence is going to be an exponential sequence. So un equals a power n times b. The first term is 3. I'm going to put a as the number I got, which is 2, and I'm going to put n as 1 in order to get b. So b is simply 3 over 2. So un is 2 power n times 3 over 2. I can simplify this by understanding that since these are multiplied, they can be written as a single fraction like this. And these can be simplified, of course, together. So 2 power n divided by 2 power 1 would be 2 power n minus 1. So we have 2 power n minus 1 times 3 as a final answer. And this is the correct final answer as well. Next, we move on to rational sequences. So you have fractions that form a sequence. Fractions are very easy to deal with. You just first deal with the numerators alone and then the denominators alone. So for the numerators, our sequence has 3, 4, 5, 6, 7. And for the denominators, we have 5, 7, 9, 11, and 13. So for the numerators, the next term is obviously going to be 8, because you're obviously adding 1 here. And then for the denominator, you're adding 2 each time. So the next term is obviously going to be 15. So the next term as a fraction is going to be 8 over 15. For the nth term, you have to solve each sequence independently. So here, you know that the formula is un equals an plus b, because this is a linear sequence. We know that the a is 1, and we put n as 1, and we put un as the first term. So the b will be 3 minus 1. We take the 1 to the other side. So b is 2. So therefore, for the upper layer, the nth term is going to be n plus 2. Remember, it's an plus b, and we said that the a is 1, so it's just n plus b, so n plus 2. Divided by, and then we work on the second layer in exactly the same way. So again, here we have an plus b equals un. We put un as the first term, we put n as 1, and we put a as the difference, which is 2, to get the b. So b is 5 minus 2, which is 3. So therefore, the bottom fraction or the denominator of the fraction is an plus b, which is basically 2n plus 2. We just solved each sequence independently as we would solve a linear sequence. You can check the video on linear sequences for more practice on this part. So 8 over 15 is correct, and n plus 2, excuse me, so I made another small mistake here. So the b is actually 3. So it's an plus b, and the b is 3, so I should have written here 3, not 2. This was a silly mistake on my part, but the concept remains clear, hopefully. And this brings us to the end of our video. I hope this has been beneficial. Thank you for watching.